Okay, so we're going to be looking at a metal bar, and it's placed between a cold reservoir and a hot reservoir, just here at the ends, like this. Alright, and it's left there for a long time, so it comes fully into equilibrium, and then it's taken from this situation and it's placed inside of an insulating material, or basically it's just thermally isolated, right? And then so it comes to a new equilibrium state under these conditions. And the question that we're asking here is what is the change in entropy for this metal bar? Alright, so let's start just by naming a few parameters real quick. I'll just draw right on this, I guess. Alright, so the bar, we're going to say, has a length of L. Alright. And a width, well, okay, rather than a width, let's use A, so it's a total cross-sectional area. Okay. All right. It has a specific heat of C sub P, a constant pressure. This is a constant pressure process, by the way. All right, so that's important. And let's see, I think that's, we also would need to know the mass density. So specific heat and mass density. That's a T. That's a T. Okay. Well, all right. So what we're going to do is we're just going to use this equation here, that the change in entropy is equal to how much heat flows, and the divided by the temperature here. All right, so let's just look at the starting situation. All right. As we put the bar in here, first you would end up with, it sort of looks like this, right? If this is temperature on this axis and X on this axis, right? This is just as we first put the bar in, okay? And this doesn't really matter for us at all. What we're more concerned with is the steady state. Okay, so here's L, here's 0, and this is the temperature, right? All right, so right, because we've left this bar in here for a really long time, so even though it may start off like something like this, this will gradually even out until it's just a straight line, just a steady state, which just means that you have as much thermal energy, right, entering. If you were to look at just a slice of the bar, there's as much coming from one direction, from the TH side, right, as there is leaving it, right? So energy is flowing through the bar, but there's just as much entering each section as there is leaving it, so each section stays at a constant temperature, and you end up with an equilibrium profile just like this. It's just a straight line. Okay, so this is what we're going to start with, and by the way, this specific heat here is just a constant. It doesn't like do anything crazy like depend on the temperature, right? Just make this easy for ourselves. All right, so I'm going to call this, well, let's just say this is, I'll just write the word initial here. All right, because here's where we start looking at the problem once this bar has come to full equilibrium with these two reservoirs. All right, and the final situation, all right, the reason we worry why this is a constant and everything like that is because then, like, once we take it out, the amount of energy is fixed. There's no more energy flowing through the bar, and what we have there is, the amount of energy is fixed, and because this is constant, basically what's going to happen is you're just going to get a uniform temperature throughout the bar. So if this is TH and this is TC, our final state here, all right, is just going to be TH plus TC divided by 2. So just the average temperature, the average between TH and TC. All right, and it's just because the temperature and the energy, because the specific heat is just a constant, doesn't depend on the temperature or anything like that. It's all just going to even itself, straight out. The energy's just going to move or flow through it until it's all evenly spread and everything's at an equal temperature, right? Because if two parts of it were at a different temperature, then heat would flow from the hot to the cold. Okay. All right. So I think we're good. All right. So just looking at this formula here, what we're going to do is first we're going to calculate this for just one tiny slice of the bar. So, if we were to draw our bar like this, we're just going to calculate it for any particular slice. It doesn't matter where. We'll just be general about it, right? We'll find the change in entropy for just one slice, and then we're going to integrate over the bar. All right. So first, let's look at what this heat, this little differential amount of heat would be, or thermal energy, whatever you want to call it. Okay. So the transfer of thermal energy. All right. So specific heat is, I guess what we're actually looking for is more of the heat capacity. So what we need to do is multiply the specific heat by the mass, and then the change in temperature. All right, but the mass is going to just be it's the infinitesimal length of the bar, so dx. We still have our CP, but first alright, so the mass is just going to be the cross-section multiplied by the length. So here's a volume multiplied by the mass density. So now we have our mass, and then we still have our CP right here, and then we have our dt. Okay, so what we need to do is first we'll find First we're going to integrate. So I'm going to bring some of these constants out front, but first we're going to integrate over the temperature for each little slice of this bar, and then we're going to integrate along the length of the bar. So bringing the constants out front, we had a CP, an A, and a rho. Okay. Now I'm going to write the integral over the length of the bar. Okay. And now let's write the integral. All right, so we need a Ti, we'll just say, to a Tf. All right, and this is just for one tiny piece again. And again, we are actually looking at this equation right here, right? So we need to divide by the big T. Okay. Let's see, I've got all these pieces accounted for, so I just need to have this. All right, so here we go. Oh yeah, so one thing we need to know is TF, all right? Well, okay, we already found TF. Let's just write that up here. So TF equals TH plus TC divided by 2, okay? And the initial, so the reason we're doing this integration first is because this initial temperature for each little slice, it depends on x, right? This is not a constant, it's just a linear equation, right? But the slope, it's easy to find the slope, right? TH minus TC divided by L. So let's write down our initial, this Ti here. Okay, I'll draw a little line right here so we'll keep these separate. All right, and we're starting at TC. Okay, I should have made my axes a little bit better. We're not starting at 0, we're starting at TC on this temperature axis here. So TC plus TH minus TC divided by L multiplied by X. All right, that's written a little bit small. Hopefully it's readable. Okay. All right, so here we go. All right, so all we have here is the natural log of temperature, right, evaluated Ti, TF. Okay. Okay, so now let's put these guys in. So let's put in the TF. Well, you know, let's just keep this, since this doesn't depend on X, I'm just going to keep this as a TF for now. But we'll just keep in mind that that's what TF is, okay? Minus natural log of, okay, so now we plug in our Ti. So we have a TC plus TH minus TC, this, and then an X divided by L. Okay. So, this term can just come straight on out because it doesn't depend on X at all. Alright, so when we integrate this, we'll just end up multiplying it by an L. Lots of parentheses in here. Okay. Alright, so now we just need to work out this integration real quick. Oh, I forgot my, I'll put my little dx out here. Okay. So just a u substitution. U equals Tc plus Th minus Tc over L multiplied by x. This, okay. Du equals Th minus Tc over L dx. Alright, so when we to swap our dx for this L divided by Th minus Tc du. Okay. And the derivative of natural log of u is just u natural log of u minus u. Okay. All right. So, kind of plugging these things in, what do we get? Again, what we're looking for is the change in entropy. Okay. CPA rho L TF minus, okay. So I'm going to kind of do this in step if I can. All right, so we're going to have this L Th minus Tc out front, and then this would turn into this integral right here. So then we would get this, but I'm going to bring that and try and substitute this back in. Okay, so I'm just going to write u ln of u minus u, except I'm going to put this in instead of u. So lots of parentheses ahead. So here's u. Now we need natural log of u, same thing again. So u ln of u Th minus Tc over L. Okay, and then the minus u. All right, this is evaluated, if we can remember, from 0 to L. All right, so those get plugged in for x. So, getting closer here. Let's go ahead and do this. So when we plug in L right here, okay, what will we get? Well, the L will divide out, and then we have just a TC plus TH minus TC, so these TCs are going to get rid of each other. So we'll just end up with a TH, okay? When we plug in a 0, then this goes away and we just end up with a TC. So we have a TH, ln of TH minus TH, and then minus TC, ln of TC minus TC. That. Okay, so here we go. I'm going to go ahead and bring this L out now. Okay, so now we just have the natural log of TF. Okay, and then minus, I'll write this as a TH over TH minus TC, natural log of TH. Okay, that's just this term right here. And we'll also do this one. I forgot another bracket out there. Okay, so this one will just be the TC, TH minus TC, natural log of TC. Alright, so now I've taken care of this term here and this term here. So we just have these two guys left. And I saved them for last because I'm going to combine them. Okay, so alright, so this one's positive, but then it goes negative again, and this one is positive. So what we're going to have is a TH minus TC, and then they're both over this TH minus TC. Alright, and it's just 1. Okay. Alright, so here is our final answer. The change in entropy for this metal bar okay, so we have this 1 plus natural log of TF. Okay, so remember what TF is. TF is just the average of the hot and cold temperatures from right up here. Okay. 1 plus natural log of TF minus TH minus C, or TC, oopsies, natural log of TH plus TC or TH minus TC, natural log of TC. Okay, let me just make sure this, yep, it checks out with what we had before. Okay, good. Alright, so draw a nice little line across here. So alright, so there we go. The change in entropy for this metal bar when it's reached a steady state. So basically all we're looking at as it has a uniform gradient from cold to hot to begin with, and then you just take that and let it just kind of even out across the whole bar, and so entropy increases as that happens, and this is the change.